This lecture is brought to you by Megger, a leading manufacturer of electrical test and measurement equipment. I've trusted Megger's equipment for years and have witnessed firsthand their commitment to education and supporting technical schools across the country. For a limited time, Megger is offering my viewers an exclusive discount on their next purchase on products sold through U.S. distributors. Simply visit us.megger.com/bigbadtech for all the details. Let's first examine motor action using our previous understanding of current flow and the associated magnetic field. The basis of a lot of motor action is that misaligned magnetic fields exert a force as they seek alignment. Norths attract souths and repel other norths, as do souths attract norths and repel other souths. Opposites attract and like repels. This explains the close bond between you and your lazy lab partner. Consider the two-dimensional cross-section of a three-dimensional loop of current-carrying wire, where conventional current enters the screen on the right and leaves the screen on the left. Our previous understanding of current magnetism demonstrates the magnetic field rotates counterclockwise on the left and clockwise on the right, such that the mutually reinforcing magnetic fields establish a north pole at the top and a south pole at the bottom. If we place this electromagnet in close proximity to another magnetic field, we'd expect them to interact. Consider what happens when we place this electromagnet inside another permanent magnetic field, oriented such that the lines of magnetism travel north to south, left to right. Given like poles repel and opposites attract, we might expect the electromagnet to be torqued clockwise as the two magnetic fields seek alignment. Let's explore the origin of this phenomenon. Note the magnetic field on the top of the left-hand conductor is opposing, whereas the magnetic field on the bottom of the left-hand conductor is aiding. These magnetic fields coalesce such that there are more lines of magnetic force on the bottom and less on the top. Unified magnetic field below the conductor acts to push the left-hand conductor upwards. Similarly, note the magnetic field on the top of the right-hand conductor is aiding, whereas the magnetic field on the bottom of the right-hand conductor is opposing. These fields coalesce so that there are less lines of magnetic force on the bottom and more on the top. The unified magnetic field on the top acts to push the right-hand conductor downwards. Given the left and right conductors are in fact cross-sections of the same three-dimensional coil, this coil will be torqued clockwise as the magnetic fields seek alignment. While it is entirely possible to explain this interaction using our previous understanding of current magnetism, it can be more succinctly explained using Fleming's left-hand motor rule, which uses the open and outstretched left hand to illustrate how a current-carrying wire in a magnetic field feels a resultant force. Extended fingers of the open left hand are oriented to the magnetic polarity, pointing north to south. The open palm is oriented such that conventional current leaves the palm. Magnetism and electricity interact to create movement. This is motor action. The outstretched thumb indicates the induced direction of movement. The left-hand motor rule applied to the left conductor demonstrates that the left conductor would be forced upwards. By all means, pause the lecture and use your left hand to confirm this. Similarly, the left-hand motor rule applied to the right conductor demonstrates the right conductor will be forced downwards. Again, by all means, pause the lecture and use your left hand to confirm this. The result being that this electromagnet would be turned clockwise as the magnetic fields seek alignment. This is the source of motor action. Electricity and magnetism are the causes, and movement is the effect. Motors use the interaction of magnetism and electricity to generate movement. Before we continue, I'd like to provide an opportunity to practice the application of Fleming's left-hand motor rule to the following three additional scenarios, where the original scenario appears in the upper left-hand corner. For the second scenario in the upper right-hand corner, consider the same external magnetic field, only this time current in the electromagnet has a reverse direction, entering on the left and leaving the right. For the third scenario in the lower left-hand corner, the external magnetic field is oriented north to south, right to left, and current in the electromagnet enters on the right and leaves the left. And finally, for the fourth scenario in the lower right-hand corner, the external magnetic field is oriented north to south, right to left, and current enters the electromagnet on the left and leaves it on the right. See if you can apply Fleming's left-hand motor rule to all these scenarios and try to determine in which direction the two-dimensional cross-section of the three-dimensional loop will be turned. By all means, pause the lecture and try this yourself. If you're tracking, you should have observed the following scenario. For the second scenario, an application of the left-hand motor rule for the left conductor demonstrates it would be forced downward, whereas the one on the right will be forced upward. This current-carrying loop would therefore be torqued counterclockwise as the electromagnet seeks alignment with the external magnetic field. For the third scenario, an application of the left-hand motor rule demonstrates the left conductor will be forced downward and the right one will be forced upward, such that the loop will be torqued counterclockwise as the electromagnetic field seeks alignment with the external magnetic field. Lastly, for the fourth scenario, an application of the left-hand motor rule for the left-hand conductor demonstrates it will be forced upward and the right one will be forced down. The loop of wire will therefore be torqued clockwise as the electromagnetic field seeks alignment with the external magnetic field. The observant among you might be drawing this conclusion. In order to swap the direction of rotation, one can change either the orientation of the magnetic field or the direction of current flow, but not both. We'll examine how this phenomenon is put to use in controlling the direction of DC motors in later lectures. Now that we've got a good understanding how magnetism and electricity create movement in motors, let's now examine how movement and magnetism create electricity in generators. This is really an application of our previous understanding of Faraday's law of electromagnetic induction, where a voltage will be induced across the terminals of a coil proportional to the rate of change of magnetism and the number of turns in the coil. Fleming's right-hand generator rule is simply a way to determine the polarity and direction of these results. Fleming's right-hand generator rule uses the open and outstretched right hand, where the thumb indicates the direction of movement and the extended fingers indicate the magnetic lines of force north to south. These are the generator's inputs: magnetism and movement. The output, electricity, is an arrow shooting straight out of the palm, where the direction of the arrow indicates the direction of conventional current flow established by the resultant induced voltage polarity. Since we've had some practice with these types of problems already, let's apply Fleming's right-hand generator rule to a couple example scenarios. Consider a conductor moving through a magnetic field, oriented such that the lines of magnetism travel north to south, left to right. This conductor is moving upwards through the magnetic field. Orient the outstretched fingers of your right hand such that the fingers point north to south. Orient the right thumb such that it points upwards in the direction of movement. Unless you got a weird-shaped right hand, your right palm should be flat on the screen. This implies that voltage will be induced such that conventional current will flow into the screen. This is generator action. Generators use the interaction of magnetism and movement to create electricity. You note in this example, we pushed the conductor upwards through a stationary magnetic field. What if we did something different and kept the conductor stationary and instead pulled the magnetic field downwards? Would anything change? Not in the slightest. Keeping the conductor stationary and moving the magnetic field down is the exact same thing as moving a conductor upwards through a stationary magnetic field. All that matters is there exists relative movement between them, and a change in magnetism exists such that a voltage is induced in the conductor. Relative movement is the key. In fact, both the magnetic field and the conductor could be moving in the same direction. As long as they move at different speeds, there will be a change. As an example, asynchronous generators, a subject we'll examine at length in later lectures, have a rotating magnetic field in the stator, and the rotor is rotating at another speed. As long as the rotor exceeds the speed of the stator, there's relative movement and generation can unfold. Just so you can get some practice with Fleming's right-hand generator rule before I blow your mind with some other content, here's a couple example scenarios. By all means, pause the lecture and use Fleming's right-hand generator rule to determine the direction of induced conventional current given the indicated direction of the magnetic field and the movement exhibited. If you're tracking, you should have observed the following results. For the first scenario, the magnetic field is oriented north to south, left to right, and the conductor is being pushed downwards through it. Orient the outstretched fingers of the right hand so that the fingers point north to south. Orient the thumb such that it points downwards in the direction of movement. Unless you got a weird-shaped right hand, your right palm should be facing you. This implies that voltage will be induced such that conventional current will flow out of the screen. The second scenario is admittedly a little odd. The magnetic field is oriented north to south, top to bottom, but it's not stationary. It's being moved rightwards at some speed. The conductor is also not stationary. It's also moving rightwards, only at a slower speed. This ultimately results in the magnetic field catching up and passing the conductor. When it does so, it's almost like the conductor was standing still and the magnetic field moved rightwards. Alternatively, this would be equivalent to keeping the magnetic field stationary and moving the conductor left. Either scenario results in relative movement between the conductor and the magnetic field. Orient the outstretched fingers of the right hand such that the right hand fingers point north to south, top to bottom. Orient the right thumb such that it points in the direction of movement. Unless you got a weird shaped right hand, your right palm should be facing you, albeit at an odd angle in your wrist. This implies that voltage will be induced such that conventional current will flow out of the screen. As I mentioned previously, this type of relative movement between a moving magnetic field and a moving conductor is also employed in squirrel cage induction motors, where a rotating magnetic field in the stator would move faster than the conductive powers in the rotor, such that current flows on the rotor without the need of physical contact or electrical connection. We'll examine squirrel cage induction motors and asynchronous generators in later lectures. Alright, now that we've got an understanding of electromagnets, Faraday's law of electromagnetic induction, Fleming's left-hand motor rule, and Fleming's right-hand generator rule, you should be at a point where you can confidently explain motor movement and generator action on an introductory level. Let's take it one step further and examine the origins of two additional phenomena: CounterElectromotive Force, or CEMF, observed in motors, and CounterTorque, or braking, observed in generators. Both of these phenomena can be thought of as an innate opposition or resistance to the effect that originally induced it. As an example of this unfolding in real life, politely ask your lazy lab partner to show up on time and prepared for class. You can be damn sure they're going to show up later, drunker, and dirtier than usual because they innately oppose your efforts to make them a functional member of society. There's a natural tendency for things to want to remain where they are, and if you want to affect some change, you got to put in some additional work. Let's examine CounterElectromotive Force first. As you are no doubt aware, the interaction of magnetism and electricity create movement. This is motor action as defined by Fleming's left-hand motor rule. My question to you is this: why does a motor winding with an at-rest resistance of, let's say, 20 ohms only draw 2 amps when operated at its rated speed when energized by a 120 volt source? An application of Ohm's law demonstrates a motor winding with an at-rest resistance of 20 ohms would ordinarily draw 6 amps when energized by a 120 volt source. This doesn't happen, but rather the motor draws, let's say, only 2 amps of current when energized by a 120 volt source. This seems a little odd, but it's an example of what can and does happen when motors operate at their rated speed. The answer is CEMF. Allow me to explain. CEMF is an oppositional voltage generated in a motor winding that opposes or is counter to the applied voltage and keeps current at a manageable level when the motor is in operation. One way to think of CEMF is as an imaginary series opposing source counter to the external source driving the motor. In our example, if we were to assume the motor winding remained at 20 ohms of resistance, which it doesn't because there's other components including inductive elements that I'm neglecting right now, a CEMF of 80 volts in opposition to the externally applied 120 volts would result in a 40 volt differential across the 20 ohm winding, thus explaining why the motor only draws 2 amps while in operation. You know that CEMF is a variable quantity dependent upon speed of the motor. At rest or 0 RPM, CEMF is 0 volts, and the source experiences no opposition, thus explaining inrush, a sudden surge of current when a motor is initially started. Whereas at the rated speed, let's say 1750 RPM, the CEMF rises to 80 volts, and the motor draws only 2 amps. The easiest way to explain CEMF is this: motor first, generator second. Motor first. Consider a conductor in a magnetic field oriented north to south, left to right. Conventional current travels into the wire. An application of Fleming's left-hand motor rule demonstrates the conductor would be forced downwards. This is motor action. Now keep your left hand on the screen. Generator second. This is now a conductor moving through a magnetic field. Overlay your right hand on the left such that the right hand fingers point north to south. Orient the right thumb such that it points downward in the direction of movement. Unless you've got weird shaped hands, your left and right hands should be back to back such that the left hand palm points into the screen and the right palm points out. This is CEMF. The secondary generator action produced as a consequence of motor action opposes the initiating effect, in this case current. Now get your hands off the screen. Everybody in the room is looking at you funny. Let's do the same thing for CounterTorque, or braking, experienced by generators. The prime movers that drive generators need to exert a measurable amount of force against an oppositional torque to produce electrical power output. And counter to a lot of incorrect thinking, prime movers don't just free spin in space. On a basic level, one can think of CounterTorque or braking as the effort necessary to move something through a magnetic field. It can be explained using similar techniques we use to explain CEMF observed in motors. The easiest way to explain countertorque or braking experienced by generators is this: generator first, motor second. Generator first. Consider a conductor moving upwards through a magnetic field oriented north to south, left to right. An application of Fleming's right-hand generator rule demonstrates that conventional current travels into the screen. This is generator action. Now keep your right hand on the screen. Motor second. This is now a current-carrying conductor inside a magnetic field. Overlay your left hand on the right such that the left-hand fingers point north to south and the palm matches the direction of conventional current flow into the screen. Unless you got weird-shaped hands, your left and right thumbs should be pointing in opposite directions. The right thumb up and the left thumb down. The secondary motor action produced as a consequence of generator action opposes the initiating effect, in this case movement. This is the countertorque or braking or oppositional drag a prime mover has to overcome to produce electrical power. Electrical power doesn't magically appear out of thin air, but rather a generator consumes the mechanical power in the form of torque and rotational speed from some other phenomenon and converts it to electrical power output. For both CEMF and countertorque, it's important to remember and differentiate between cause and effect. A motor initiates movement because of current and magnetism. CEMF is secondary because induced movement interacts with existing magnetism to oppose initiating current. Similarly, a generator induces current because of movement and magnetism. Countertorque is secondary because induced current interacts with existing magnetism to oppose initiating movement. Long story short, CEMF and countertorque mean the real world opposes your efforts to change it, and if you want the world to change, you got to put in the work. Alright, I believe we accomplished what we intended to do in this lecture, and more. In conclusion, this lecture examined fundamental interactions between magnetism, electricity, and movement for rotating electrical machines, motors, and generators. We introduced and discussed electromagnets, Faraday's law of electromagnetic induction, Fleming's left-hand motor rule, and Fleming's right-hand generator rule. Additionally, we discussed CounterElectromotive Force, or CEMF, experienced by motors, and countertorque, or braking, experienced by generators. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest. We'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.